Assalamu alaikum wa rahmatullahi wa barakatuh. Hello everyone, welcome to lecture 23, Organic Chemistry 2. Today we will continue on Aldehyde and Ketone chapter 4. We will cover the synthesis strategies, principles of organic synthesis. A multi-step synthesis of any organic compound requires a chemist to accomplish three related tasks. The first task is constructing the carbon framework or skeleton of desired molecule. Task 2, introducing, removing, and transforming function groups in a fashion that achieves the functionality of the desired compound. Task 3, exercising selective stereo control at all stages, in which centers of stereoisomerism are created or influenced. The assembly of the molecular framework will depend on part on the structure and functionality of available starting material, the selectivity, ratio, and stereo of the various reactions that may be used to stitch them together, and the loss and relocation of functional groups in the intermediate compounds formed on the way to the final product. We have two ways to construct the framework: linear synthesis, which will be starting from A to B to C to D to E to F target molecule. Or we can use convergent synthesis, that we can build up starting material independent and then combine them together, like A to B to C, and then KLM, and then get C and M to construct F. This is called convergent synthesis, and it's shorter and more efficient than linear synthesis, leading to a higher overall yield. See, if the A to B is 80 and B to C is 80, etc., we can multiply. We have here 1, 2, 3, 4, 5 steps times 80, and we get that the overall yield is 32.7%. While in convergent synthesis, 80, 80, so when we have here C and then 80, 80 to M, and C to M 80, we can get the overall yield 51.2. So we multiply 80 times 80 times 80, and that's it. The synthetic plan generated from the retrosynthesis analysis will be a roadmap to guide the synthesis for the target molecule. Do we have symbols for retrosynthesis analysis? Yes. The disconnection, we use wave line. For retro arrow, we use this arrow. The open arrow represents going from target molecule backward to similar molecule. We call it retrons. Function group interconversion, FGI, describe a process of converting one function group to another. After we're done with the retrosynthetic, we use this synthetic arrow that we used in organic 1 and organic 2, okay, for the synthesis of any compound. This cross arrow represents going in a forward direction. Show the retrosynthetic analysis of mascaler, the pheromone of the domestic housefly. It is cis-alkene. This cis-alkene we can get from alkyne, so it's function group interconversion from double bond to triple bond, and we know that we can reduce the triple to cis using Lindlar catalyst and hydrogen. Now, to build up this alkyne, we can get this connection. Here will be negative and here will be positive, and we call this synthon. And the synthetic equivalent of this anion will be terminal acetylene, and this cation will be, the synthetic equivalent will be alkyl halide. We can do again this connection from this side. We get this negative and this is positive. Again, the sensor will be acetylene and alkyl halide. As we mentioned, this is a disconnection. This is plus, this is minus. We call this symptoms, and this alkyl halide will be synthetic equivalent to the carbocation, and this terminal acetylene will be the synthetic equivalent for this anion. And we can give this retron. We can call them retron. Direct synthesis, we start now from acetylene, one equivalent N-butyl lithium, followed by alkyl halide. We get this new terminal acetylene. Again, one equivalent N-butyl lithium, alkyl bromide. We get this acetylene compound or acetylenic derivative or alkyne with the same number of the target molecule. All what we need now is to transfer the triple bond to cis double bond using Lender catalyst with hydrogen. We get the target molecule. We have another method, retrosynthetic analysis, for this compound. We can disconnect in here. One will be positive and the other carbon will be negative. Synthetic equivalent of the positive will be the carbonyl, and the negative charge will be this yellow, which we can obtain from the alkyl halide with triphenylphosphine. We can get this aldehyde from commercially available alcohol, primary alcohol, this compound. So C9 alkyl bromide with triphenylphosphine will provide the phosphonium salt, which reacts with N-butyl lithium to give the yellow A. The C14 primary alcohol with pyridinium chlorochromate will give the aldehyde B. Reacting A with B will give you the target molecule. But notice that there is no stereo control over the final product. We get cis and trans. Comparing the two synthetic pathways show that while the Wittig route is convergent, the stereochemistry of the double bond is not stereospecifically controlled. The linear pathway of the stereospecific partial reduction of the alkyne is then preferred route to masculine. Propose an efficient synthesis of the following transformation. This alkane to that one. We notice that we have two extra carbons from the starting molecule. So to build up extra carbons, let's see how we can do that. Alkene. We can get the alkene from alcohol. And the alcohol, secondary alcohol, we can get from carbonyl. So this connection in here, this will be negative and this will be positive. So equivalent to this will be the ethyl magnesium bromide, and for this plus will be the aldehyde. And we can get the aldehyde from primary alcohol, which we can obtain from the given alkene by hydration. And we notice that the OH will be on the carbon carrying more hydrogen, so that will be anti-Markovnikov addition, boration followed by oxidation. This is a retrosynthetic approach one. Let's see the synthetic pathway. So we start with this starting material, boration, hydrogen peroxide in base, we get the primary alcohol, pyridinium chlorochromate oxidation, primary alcohol to an aldehyde, then react this with ethyl magnesium bromide, we get the salt. Upon hydrolysis, we get this alcohol. OH is not good leaving group, so what we have to transfer it to tosyl or tosylation using tosyl chloride pyridine, we get O-tosyl. Then we add base. The base will take this hydrogen via elimination A2 mechanism to get the alkene. As you can see, this is going all the way up. That's linear synthesis. Well, retrosynthetic analysis 2, we can cut in here. This is negative, this is positive. So we can get this from the carbonyl. And the negative, we get it from the yellow. We know that if this is single bond, that will be negative positive. If this is single bond, this will be positive negative. And we can get this ketone upon ozonolysis of the starting material. This is convergent method. The phosphonium or the phosphine unit we can obtain from alkyl bromide, triphenylphosphine, followed by treatment with base like n-butyl lithium. So starting with this alkene, ozonolysis followed by dimethyl sulfide treatment will give you the cyclohexanone react with the yellow to give the target molecule. We have discovered now two plausible methods. Both methods are correct answers to this problem, but the method employing the Wettig reaction is likely to be more efficient because it requires fewer steps. Propose a synthesis of the major component in one common oral contraceptive preparation. Innovate. Use as your starting compound nortesterone derivative. This is a starting material, and this is your target molecule. Here is carbonyl function group, here is carbonyl, here is alkene, here is alkene, here is OH, but here is OH plus extra alkynyl unit. So how we can add this part? We can add this part when we have here carbonyl. Okay, if we oxidize this, let's see, retrosynthetically, we will say, okay, we cut in here this connection, and this will be negative and this will be positive. So the equivalent here will be the ketone, and the equivalent here will be terminal alkyne. We can get this from the OH via oxidation. But this approach, we have here this, let's say, this compound we prepare, it can react with this carbonyl and that one. So we cannot control actually this reaction. So this approach is wrong. What to do? We need first to protect, so we can get this from the protected one, and we can get this one now from the reaction of the acetylide with carbonyl, right? To get, and we can get this from the alcohol, and this alcohol with a protected carbonyl, we can get it from our starting material available. So doing the synthesis, first step is to protect this carbonyl, oxidize this OH with pyridinium chlorochromate and dichloromethane. We react this with acetylide, add it, no problem. Now we hydrolyze this back to carbonyl acidified water. We get the target molecule. See you next lecture. Bye bye.